Thank you very much. Okay, many thanks to the organizers for the chance to appear today. I'll be talking about work that I did just at the very end of my PhD at Harvard. I actually just moved to start a postdoc at Cornell. In short, what we'll be dealing with today are basically local microscopy measurements on an analog of magic angle bilayer graphene, which is actually magic angle twisted trilayer graphene, which I'll introduce. But as we'll see, this is kind of an interesting system where there's kind of two species of electrons. There's flat bands, but then there are also dispersive bands. And as we'll see, the topological structure of these bands plays quite an important role in our ability to disentangle their contributions to the interaction-driven physics in this system. Let me just begin by acknowledging the efforts of many talented people who contributed to this work and made it possible. In particular, Yonglong's a postdoc who I worked with closely on this experiment and many others. The device that I'll be discussing was actually fabricated by Jungmin Park from Pablo Herrero's group. And all along the way, we've really benefited from extensive collaboration and really help understanding the physics here from the group of Ashwin Vishwanath. Great. Let me just begin by introducing the basic properties of magic angle twisted bilayer graphene that attracted so much attention a couple years back. So of course, the kind of system that we're looking at here, we can imagine two graphene sheets that are just overlaid on one another with a small twist angle, right, which gives rise to this long wavelength superlattice pattern that we call a moiré pattern. Now, famously, if one chooses just the right magic angle for these two bands, the hybridization between the two bands actually can give rise to low energy bands that are extremely flat. Okay, so this is kind of a single particle calculation of the sort of band structure one would expect around the so-called magic angle of about 1.1 degrees. And by now, the consequences of this too are quite famous. You can observe superconductivity and so-called correlated insulating states in this groundbreaking work from Pablo's group. And how do we understand this? Well, what we understand is that near the so-called magic angle, where the bands become so flat, one can enter a regime readily where the energy scale of the interactions basically dominates the bandwidth. So we're kind of in a situation where the potential energy is way larger than the kinetic energy. You can kind of visualize that on this plot here, which is kind of comparing the bandwidth with an estimate of the interaction energy. But anyway, the lesson here is that it looks like this is a really rich system in which one can realize some really interesting interaction-driven states. Now, there's a kind of a long tradition in condensed matter physics, I would say. If you find a material that's of interest, then try to find analog materials that might be able to teach you even more. It was kind of interesting in the first couple of years after people first observed the superconductivity that it seemed to be kind of difficult to see it in every structure. Every sample behaves a little bit differently. And so it was quite a welcome surprise when a different material was studied, so-called twisted trilayer graphene, that seems to give somewhat more robust and more reproducible superconductivity. So in particular, the structure that I'll be discussing now and that we'll be discussing in most of the talk is shown in this little cartoon picture. Specifically, the top and bottom graphenes we can assume to be kind of in perfect registry, but it's the middle layer that is rotated with respect to both of them. Importantly, this endows the system with a mirror symmetry that, as we will see, has important consequences. Okay, and so the kind of remarkable thing about the structure is that it exhibits superconductivity over a rather vast part of the phase diagram. Okay, so these are two plots just of the longitudinal resistivity and a kind of Hall bar geometry. Plotted as a function of the moiré, the electron density in terms of moiré filling factor, so that's electrons per moiré unit cell along the x-axis. I should note that as with monolayer graphene, there's an approximate four-fold symmetry here, so each band can carry 4 electrons, and so this basically +4 is the point at which one has fully filled the low energy flat bands. -4 means that they're fully emptied. And then along the y-axis here is the displacement field. So you're kind of imagining a structure where there's a top and bottom gate. We can tune both the density and the electric field that's applied to the graphene independently. And so this is the work from Pablo's group. Similar results were obtained in Philip Kim's group as well. One observes really robust superconductivity with generally higher TCs than were originally observed in the magic angle twisted bilayer case. Okay, so it's interesting that one can seem to realize more robust superconductivity in this system than in twisted bilayer graphene. That begs the question of whether there's a fundamental difference between the superconductivity in this system, or what is the mechanism that allows it to become more stable here. Now, in terms of the electronic structure of these materials, it's worth noting, as I mentioned, that the mirror symmetry has some important consequences for the low energy band structure. Now, before in the twisted bilayer case, we noticed that near the magic angle there are two rather well separated bands from the remote bands that have an extremely low bandwidth. In this case, because of the mirror symmetry, we can kind of actually intuit what sort of band structure we should expect in this system. If we really have perfect mirror symmetry between the top and bottom, I can decompose the system into mirror symmetric and mirror antisymmetric components. And since I have an odd number of layers, the mirror antisymmetric component cannot have any weight on the middle layer. And so really, in this kind of mirror symmetric sector, you're just seeing two perfectly aligned graphene sheets. So that really sounds like you should get something that just looks like the band structure of monolayer graphene. Indeed, if you go through and do a kind of more complete continuum model calculation, that's exactly what you find. One finds, if I look first at the orange here, that for zero displacement field, where the mirror symmetry of the system is intact, I get some flat bands that look very much like the flat bands of twisted bilayer graphene. But I also get this extra, basically Dirac cone that comes in at one of the mini-Brillouin zone valleys. And these two bands are essentially decoupled from each other at zero displacement field. Okay, now what happens is that if I turn on a finite displacement field, then the mirror symmetry is broken, and the two sectors, the mirror symmetric and antisymmetric, can hybridize, which gives rise basically to something that looks like the flat bands, but with a slightly enhanced bandwidth due to the hybridization. Good. So it's certainly interesting that the superconductivity in this system appears to be stronger, and what's even more kind of striking is that this trend seems to continue and continue as the number of layers of graphene increases. So these are kind of a highlight of three works that came out around last December and January, each of which investigated basically magic angle variants with 4 and 5 graphene layers. And the general conclusion of each of these works, so this one from the Caltech group, this one from Pablo's group, and this from the group of Emmanuel Tutuk. The general conclusion here is that as one increases the layer number, it looks like superconductivity begins to kind of win out over all the other insulating phases that are present in the system. And so what we really want to do then is to ask the question of what the role of the additional bands that start to get added as we increase the layer number is. I haven't shown here a kind of band structure that you expect for 4 and 5 layers, but applying the similar arguments to what I gave for the kind of monolayer Dirac cone and trilayer graphene, you can conclude that these 4 and 5 layer variants also have additional kind of dispersive bands that overlap with the flat bands and yet do not seem to interfere with superconductivity. So that's the problem that I want to pose for the remainder of the talk. The problem is to try to disentangle the contributions of these additional dispersive bands in these higher layer number structures, try to understand what their role is in the interactions, and in particular, the interaction-driven insulating states. That's what we'll be focusing on. And what's more, we'd like to find out, is there any regime in which we can make the interactions between these two sectors of the system strong? Because we know that there's lots of interesting physics that can come about when one couples, for example, heavy electrons and light electrons. One can get Kondo effect and so on. We certainly haven't seen that kind of thing, but it will be a very interesting direction for future research, and one that's been discussed in some of the theory literature so far as well. Good. So with that introduction, let me give a little bit of background on the experimental technique that we'll be using to perform these studies. The technique is known as scanning single electron transistor microscopy. So as with many experimental techniques, it involves bringing some kind of sharp tip very close to a sample. In our case, it's a tip of about 100 nanometers in diameter at the end. But this tip is kind of special in the sense that it's not a kind of metallic STM tip, but instead it's a tip with a device fabricated on the very end of this 100 nanometer taper. And the structure of this device is that it consists of two electrodes that run along the sides of the tip that are actually only tunnel coupled to a metallic island at the very end of the tip. So actually, this structure behaves as a quantum dot, if you like. It's a single electron transistor. And I'll explain in a moment the Coulomb blockade principle according to which this device operates. And the rest of our experimental geometry will be studying kind of a twisted, I wrote TBG here, I should have written TTG, sorry. We'll be adding electrons to the system with a backgate, kind of shown as this yellow bar here. This is what the tip kind of looks like in reality. It's about 17 millimeters long. And so the way this device works is that according to the Coulomb blockade principle, if one has a single electron transistor, a device where the energy cost of adding a single electron is significant, it will exhibit Coulomb blockade oscillations that correspond to basically adding one electron to the metallic island at the end of the tip. So in particular, we can monitor the current flowing through the tip as we change the local electrostatic potential. And we see that at certain points there's a peak in the current. And these correspond to configurations, or basically values of phi, for which the configuration with n and n plus 1 electrons is nearly equal in energy, which means that electrons can hop on and off the island. On the other hand, away from these degeneracy points, one sees dips in the current. At these points, the system really prefers to have a specific n number of electrons, and so hopping on and off the SET is forbidden. These are the so-called Coulomb blockade oscillations, and the principle of our technique is simply to monitor their evolution as we change the local electrostatic potential by doping the graphene. So what happens is we add electrons to our graphene sample. As we add electrons to the graphene, the local chemical potential changes, and in equilibrium, in the absence of any bias currents, any change in chemical potential must be canceled by a change in electrostatic potential. And so using this technique, we can directly measure, actually, the chemical potential locally in a two-dimensional system of interest. Okay? And in particular, in what follows, we'll really be looking at gap states, so kind of incompressible states, as we call them, or states where we see a sudden step in chemical potential. And the value of this step in chemical potential, we would just interpret as the value of the gap for that state. In practice, we will make use of an AC lock-in technique, so we measure not mu of n, but instead d mu dn, the derivative with respect to density. And I'm showing you this because we'll see many plots in what follows of this quantity. What you should think is that if we're looking at d mu dn, then any peak in that quantity corresponds to a gap state. And so we'll kind of use this principle to interpret the phase diagrams of twisted trilayer graphene that we observe. Okay? I don't want to do too much advertising. Let me just mention that this technique was used extensively in a number of works in Amir Yacobi's group in years past. You can see really fragile fractional quantum Hall states in graphene. This is a nice work from Ben Feldman a few years ago. What's really interesting is that you can actually directly observe the fractional charge of quasiparticles in, say, the 1/3 fractional quantum Hall state. So these are kind of measurements of actually the charging of localized states in a system. So these are kind of charge puddles in some gallium arsenide quantum well. And what you see is that if you go to the filling factor 1/3 regime, so these kind of numbers in the box are meant to be filling factor. This is a nu equals 1 quantum Hall state. This is a nu equals 1/3. It turns out that basically in this 1/3 state, you can see these fringes that correspond to adding one quasiparticle, and there are 3 times as many fringes. And without going into too much details, that was basically interpreted to mean that the quasiparticles carry 1/3 of an electron charge, which is thought to be true for filling factor 1/3. we can also study some kind of interesting quantum Hall ferromagnets where we are able to measure a magnon chemical potential, but let me not get into that right now. Okay, so now let me move on and describe some of the basic properties of the device that we studied. Okay, so this is just an image of the device over here. So it's kind of a long Hall bar geometry. And if we measure the RXX, the kind of transport in a longitudinal configuration where current's flowing from the right to the left, using different pairs of contacts, we can verify that this device exhibits kind of the hallmarks of interaction-driven physics and twisted trilayer graphene. In particular, if I look at this top plot, as I lower the temperature down to about half a Kelvin, we can see that there are pockets of superconductivity developing near filling -2, so that's -2, basically 2 holes per moiré unit cell. And we can also see some kind of weak change in resistance on the electron side. If we measure down to lower temperature using a different pair of contacts, well, at different positions, the twist angle is a little bit different, and one can see a little bit of variability. For example, at this particular position between fillings 3 and 4, here, it seems like the superconductivity on the electron side is somewhat stronger than that on the hole side. But anyway, these are basically the kind of hallmarks that we expect from twisted trilayer graphene. However, as regards the insulating states, and this seems to be true in most of the studies of this material so far, transport is kind of ambiguous. Okay, it seems like there are some kind of regions at higher temperature over which RXX may be increasing, but at low temperature, one doesn't really observe clear signs of insulating behavior. As we'll see, that's in sharp contrast to what we observe in the local compressibility measurements. Okay, so now let's finally move on and compare this with what we see when we use our scanning single electron transistor tip to look at the compressibility locally. Okay, so I'm going to focus on this region 2 up here, well, this position 2. This is where we saw this kind of superconductivity, but no clear insulating states in transport. Okay, and so this is an experimental data set showing this quantity d mu dn, okay, measured at the base temperature of the cryostat of about half a Kelvin as a function of magnetic field. And so let me just, this sort of data is not very familiar, but let me kind of begin by just describing the salient features here. So probably the most salient feature is that one can observe a series of peaks that have slopes. That is, as one increases the magnetic field, the density at which they occur changes. Okay? Now, from what I told you before, anytime I see a peak in this quantity d mu dn, that should correspond to an incompressible state, a state with an energy gap. Okay? So that means that we can identify all of these peaks really stable down to 0 magnetic field for many of them as insulators, as incompressible states that were not observable directly in transport. Okay? Now, what's interesting is that the slope that I mentioned actually encodes the kind of intrinsic topology of that particular ground state. Okay, there's something called this strata relation, an old formula, according to which the density at which a particular incompressible state occurs should change linearly with the Chern number as one increases the magnetic field. Okay, so what that means is that all of these gaps that we see with slopes, they're basically Chern states. They're states with a non-zero Chern number, and in principle they would have edge states. Whether we can see that in transport might be limited by disorder, but clearly they are manifested in the local compressibility. Okay? So clearly there's kind of topological states, incompressible states all over the place here, despite the fact that they're not apparent in transport. I want to also mention some other more subtle features. One is that if you look on the hole side here, I'm kind of trying to trace out this feature, there's kind of a slow modulation of this background value of d mu dn. You can see these kind of white stripes that kind of start in the middle of between, say, -2 and -1, and then disperse upward with a slight slope. These features were previously observed in twisted bilayer graphene, actually. I won't go into too much detail about them, but they're basically thought to result from some gradual so-called isospin transitions. But by isospin, I just mean the combined spin-valley symmetry. So at these points, basically one thinks that one of the kind of spin valley flavors is being fully filled or fully emptied as you get closer to the integer filling. Okay, and finally, I just want to mention that this quantity d mu dn, if you kind of take a single particle calculation, it's always positive because you just have a Fermi C filling, and so there's no way to reduce the energy if you add particles. But already at the simplest level of Hartree-Fock, it's possible to get negative compressibility in low-density systems if the interactions are strong enough. And actually, we can observe kind of a remarkable feature near charge neutrality. So there are these kind of bold blue lines here. Those are regions where the electronic compressibility is actually strongly negative. Actually, the value of the negative compressibility there is as big or even larger than some of the gaps that we see. Okay, and so this is kind of a signal that, to my knowledge, was never observed in any moiré system before. It seems to be I should say, negative compressibility has been observed, but not in this kind of fourfold pattern near charge neutrality. And so this seems to indicate that there's some kind of really strong interactions taking place near charge neutrality in this system. And we'll return to that feature near the end of the talk. Sorry? I'm sorry, I didn't hear that.
Can C take on rational values?
Which one, the blue?
No, C.
Oh, no, that's an integer. Yeah, so it's, for a fractional quantum Hall state, I mean, I don't want to call a Cher number a fraction because, a Cher number is supposed to be an integer, but in some previous work, we observed kind of a fractional value of C. So a fractional quantum Hall state, for example, would follow a slope of 1/3. And you can see that, you can see that in fractional quantum Hall states. You can also see it in so-called fractional Chern insulator states, where in some previous work that I can show you later if you're interested, we kind of took a situation where we isolate one of these bands and fill it 1/3 of the way, and then you can see an incompressible state that is analogous to a fractional quantum Hall state, but without Landau levels. Yeah. Thanks. So now what I'd like to do is kind of try to understand the sequence of Chern numbers that is observed in the experiment in a little bit more detail, okay? And to understand this, I want to actually go back to what I was just describing in terms of in response to the question, just to say a little bit about how this works in twisted bilayer graphene. So I think actually twisted bilayer graphene is a pretty appropriate material for this conference. It's no doubt a material with strong interactions, but it's also got intrinsic topological bands. Okay? Now, I have here a cartoon that's meant to represent the kind of low energy band structure of twisted bilayer graphene. If we don't break the so-called C2 and T symmetries, T is time reversal, of course. C2 is basically the sublattice symmetry, the 180-degree rotation symmetry. Analogous to monolayer graphene, if you don't break C2T, you can't gap out the Dirac points, okay? And so what I have is, basically I can't fill any of these bands individually. I can't really access the kind of intrinsic topology that I have at the Dirac points. But if I break one of these two symmetries, let's say we break time reversal symmetry, say by kind of turning on a Haldane mass or something like that, now you can get Chern bands. And in particular, what is commonly observed in this system is that one can get a level ordering that looks something like this, where, for example, depending on the sign of the mass term, say, I can have all Chern -1 bands as the conduction bands and all Chern +1 bands as the valence bands. Okay, and so as a result of this, you can observe kind of this canonical, I call it, sequence of Chern numbers in magic angle twisted bilayer graphene. So this is some beautiful work from Andrea Young's group, where they measure resistance, longitudinal resistance as a function of magnetic field and filling factor here. And let's try to understand the sequence of topological states they observe. So there's a very salient feature coming from filling factor 1 here. Okay, and if you go in and measure what the slope is, they find that it's a Chern 3. Okay, and so then the question is, can I construct a Chern 3 from this kind of a basis that I've given you here on the left? And so to get to filling factor 1, that means I have to fill 5 out of 8 bands. That's because the kind of intercept here on the x-axis is basically the number of bands that's filled. Okay, so it's easy to get to a total filling factor of 3, a total churn number of 3. I can just fill all of the churn plus 1 bands and just one of the churn minus 1 bands. Now, at a single particle level, that might not work because, well, I can't just open up a gap, but because of interactions, it's readily observed in twisted bilayer graphene that one can put in 1 electron per moiré unit cell, and the system will be happy to open up a gap due to exchange. Okay, and so you can go through the same construction for this churn 2, say, and you can, if you just kind of choose a different sign for the mass, you can get these kind of states on the whole side as well. And I should say you can, if you don't like this kind of churn band picture, which is valid at low magnetic field, you can also arrive at similar conclusions by calculating a full kind of Hofstadter spectrum for the problem. Okay, now the question is, what does this have to do at all with all the measurements that I was just showing you on twisted trilayer graphene? Well, the idea is to kind of try to catalog the states that we observe in twisted trilayer graphene. So this is just what that data looked like. And if I go in and compare the churn numbers with twisted bilayer graphene, they're rather different. Okay, instead of, for example, if I go to filling factor 1, in twisted bilayer we had this kind of prominent churn 3. Here instead I get a churn 5. Okay, and if I go and check a few other filling factors, I guess it's not seen in this data, but people often see a churn number of 1 from filling factor 3. We see a churn number of 3 prominently instead. Okay? So this is maybe a little bit surprising. After all, I told you on the first slide that it looks like twisted trilayer graphene is just twisted bilayer graphene with a Dirac cone superposed on top. And we can actually use this principle to make sense of the churn numbers that are observed in the experiment. This is just a more complete diagram showing all of the kind of principal churn insulators that we observe in the experiment. And if you stare at this long enough, you can kind of realize that most of the churn numbers we see are kind of offset by 2 relative to a churn number that's commonly observed in twisted bilayer graphene. Okay, and so how can we understand this? Well, let's just think about the low energy properties of the system again. So what happens as we turn on a magnetic field, this is just a cartoon, it's not a serious calculation, but it's basically agrees with serious calculations. What happens is that at 0 magnetic field, the system consists only of the 2 flat bands plus this kind of monolayer Dirac cone. But things change very quickly as one increases the magnetic field, mainly because of the high velocity of the Dirac cone. It's well known that in monolayer graphene, one can get giant cyclotron splittings basically because of the large Fermi velocity of the system. And so as we increase the magnetic field, what is shown in black in these kind of lines that follow square root trajectories are the degenerate Landau levels of the monolayer graphene. And very quickly, just at a few Tesla, all but the n equals 0 Landau level of monolayer graphene will be well beyond the flat bands and won't be relevant to the problem at all. Okay? On the other hand, in the red, there's not much evolution of the flat bands themselves. The only thing that really happens that's noteworthy is that one can start to observe the 2 n equals 0 Landau levels that are associated with the 2, basically the bilayer graphene sector of the twisted trilayer graphene. Okay? Now, so there's a lot of churn numbers up here, but basically what is important about this plot is that there's this n equals 0 Landau level from monolayer graphene that gets left behind. Now, monolayer graphene follows this kind of famous sequence of, kind of anomalous sequence of Hall plateau. You see first, because of the fourfold degeneracy, you actually see incompressible states at -6, filling -6, then -2, then 2, and then 6. And so this actually starts to sound like this offset in the churn numbers of 2 that was observed in the churn numbers for twisted trilayer graphene. Okay, so more specifically, let's just take an example of, again, this state that we saw from filling 1, so at, with the x-intercept of 1, that we said had a total churn number of 5. Okay, now I told you that if we just kind of follow this so-called canonical sequence that I outlined, one would conclude, or one would expect that you would get a prominent Chern insulator with a Chern number of +3, because I can fill up 4 of the Chern +1 bands and 1 of the Chern -1 bands. Okay? Now, if we just add this offset that I mentioned from the n equals 0 sector, then we can get to the total Chern number of +5. And we can reconstruct all of the states that are observed in the experiment by combining basically this ±2 offset with a ground state that has been observed in magic angle twisted bilayer graphene. There's some subtleties that some of these states require a kind of symmetry breaking mechanism. A translation symmetry breaking mechanism. I won't say too much about that unless people are interested in it. I'll be happy to answer questions. What this kind of suggests is that it looks like the two spectra are just on top of each other. Okay, so I didn't have to kind of invoke any spooky or interesting interactions to arrive at these conclusions. What's more, we can show actually directly using the experiment that our measurements of d mu dn are very consistent with this kind of spectrum. Okay, so without going into too many details on the sort of analysis we did, we kind of borrowed a procedure that was first, to my knowledge, described in a work from Ben Feldman's group at Stanford. They also do kind of local compressibility measurements. Since we're measuring directly d mu dn and hence mu as a function of density, well, mu is kind of like, that's what the Fermi level is, and we're also measuring d mu dn, which is the inverse of the density of states. And so if you kind of imagine collapsing, these traces are comprised of many data points. The way our measurement works, each point corresponds to a fixed number of electrons that's being added to the system. And so if we just collapse these traces onto a single axis, then that's kind of a measure of the density of states as a function of Fermi level. And if we follow this procedure, we can kind of generate these interesting looking spectra, which, if you like, corresponds to something like a thermodynamic density of states rather than something like a tunneling density of states, where you can see many of the salient features that I tried to highlight in that red and black cartoon from the last slide. Okay, you can see, first of all, there are big gaps in the spectra that correspond to the remote gaps of the system when one has fully filled or fully emptied the flat bands. You can see this kind of fourfold degeneracy of the flat bands themselves, and you can see some feature from charge neutrality corresponding to the Landau levels of the flat bands. And you can see some rapidly dispersing features here that are highlighted in red that correspond to the n greater than 1 Landau levels of the monolayer graphene. Okay? So it agrees well with this kind of picture. And so what's interesting is that not only does it look like I didn't have to invoke any kind of unusual interactions, Coulomb interactions between the light Dirac cone and the flat bands, I also seem to be able to describe everything without having any displacement field at all, which is kind of interesting because actually in our geometry we can't control the displacement field. We have to come in with the tip to sense the local electrostatic potential. If we had a top gate, that would block the signal that we need to measure. And so it's kind of a little bit surprising that despite the fact that we're presumably applying a finite displacement field to the system, since we only have a backgate, we can still describe all the physics we see just in a basically mirror symmetric d equals 0 picture. Okay? So this all is suggestive, but I would say there's kind of no smoking gun in what I've shown so far that the Dirac electrons are really not directly participating in the interactions, okay? So there's something that's a little bit unusual about this. I'm focusing now on the incompressible states that are observed at each of the integer fillings, okay? They're stable down to 0 magnetic field. And this is a little bit surprising because we know that there should be this kind of Dirac cone that's always in the background, right? So the picture that I've given you so far is that, well, it looks like the flat bands interact just as they interacted in magic angle twisted bilayer graphene, and the Dirac cone's just along for the ride. And if that's the picture, then it's surprising that we have a gap at all, because it sounds like the Dirac cone should basically span the gap that's opened in the flat band sector. Okay? Now, at high magnetic field, there's no problem because the Landau levels are pushed out beyond the bandwidth of the flat bands. But at low magnetic field, one would expect to see signatures clearly in the gaps at each of the integer fillings. You can see kind of a weak modulation in some of them, but the more prominent feature is this kind of density shift that occurs. In particular, the black lines that I've drawn on each of these traces are basically the trajectory that one would expect for if that state followed the exact Chern number that we assigned it at high magnetic field. And so this kind of density shift at low magnetic field is unexplained. Okay? So with this question in mind of what are the Dirac fermions, this kind of light Dirac mode, what is it doing as we enter the gap state? I'd like to just point out that the answer to this is kind of ambiguous from the literature so far. In the case of the transport studies, one can see signatures of gap openings at elevated values of displacement field by analyzing the Hall density. So these boundaries were kind of concluded by putting a small magnetic field and then seeing how the Hall density changes as you change the density. But the kind of direct evidence in terms of a like diverging resistance is never terribly clear in transport. I should also mention that there's a study from Dmitry Efetov's group that can observe the Landau levels coming in through the gap, but the behavior at low magnetic field is unclear. And this is in contrast to what we see where there's clear gaps at the integers, and also in contrast to what has been seen in STM studies. This is a nice work from the Caltech group where they did some beautiful work on especially the superconducting state on the whole dope side. And they can also see, it's STM, so you're looking at single particle gaps. They see a gap where you expect the correlated insulator. It's, of course, a little bit, one has to disentangle, and one has to distinguish what is a superconducting gap versus an insulating gap in STM. They can do that by looking at the appearance of some kind of Coulomb diamond, some charging features in the insulating state. But this kind of conclusion is really at odds with this idea that you should see that the Dirac mode should span the gap, because you can't really get a fully incompressible state as is suggested by the STM if there's kind of some density of states left behind. Okay. So what I want to do now, time is getting a little bit short, but what I want to do is try to answer the question of how to identify a true incompressible state, that is kind of zero density of states, versus just a state with a low density of states. A suggestive answer was provided in actually this work, some work related to what I mentioned on this measuring the 1/3 quasi-particle charge in gallium arsenide. Let's imagine a situation where there's kind of a built-in kind of disorder potential in the system. Okay, so normally if a system can screen, the electrons will reposition themselves as to cancel out the disorder potential. But if one has a kind of an incompressible system where you cannot just redistribute the electron charge as in the quantum Hall state, then one will end up with basically regions where the electrons cannot fully kind of equilibrate with the potential, and so that leaves quantum dots basically that are left behind in the system. Okay, so you can kind of imagine what this would look like as one approaches the integer filling for an integer quantum Hall state. There are pockets where the system remains doped, and these act as kind of as quantum dots, and we can actually see the charging of each of those quantum dots microscopically with the scanning single electron transistor probe. And so in particular, what was done in this work was to actually resolve these big incompressible peaks, similar to what I showed in this kind of field sweep measurement, into actually individual incompressible peaks associated with charging just a single disorder site near the SET. And this is kind of if you like, this is the microscopic nature of what these insulating states are. They're kind of pockets of charge that no matter how clean you grow your gallium arsenide, they're always there. And one has to charge them up one by one as you go through the phase transition. Okay, and let me not go into too much details on this. But in short, we try to apply the same principle as a method for distinguishing a true incompressible ground state from a state that merely has a low density of states. These plots are, again, measurements of this quantity, basically something that's proportional to d mu dn, as a function of magnetic field and density. And what you can see here is that there are discrete lines at high magnetic field that correspond, we think, to basically charging up a single sort of charge puddle near the SET. Remarkably, what we see is that at low magnetic field, they disappear rather abruptly, where these kind of bands of compressibility cut through. And in some cases, we can even recover these kind of localized states as we decrease the magnetic field before they disappear for good at zero magnetic field. And the way we interpret this is that at high magnetic field, there are no electrons from these kind of light Dirac modes at the Fermi level available to screen out the local electrostatic potential that's generated as one adds electrons to these discrete charging puddles. Okay? But on the other hand, when the Landau levels come in and approach, is basically when the Dirac fermions from the light modes are present at the Fermi level, they can screen, and so as a result, it's not possible to have these localized charge puddles. The system is just compressible. Okay, and so this is it's a better metric than just looking at a peak in d mu dn as a way to identify a gap state. This kind of question of whether a state can support localized states is it's a binary, it's a yes or no. And so what we can argue based on this is that, well, it looks like at low magnetic field, you don't have a true gap. Instead, you just have a system where the Dirac fermions kind of span the gap, and they may slightly change the value of the gap in a kind of Thomas Fermi approximation, but there are no true incompressible insulating states at zero magnetic field in this system that we've seen so far. Okay? And I won't say too much. These are just the density shifts that are observed, which we could attribute to the number of Dirac electrons that are doped into the system. Now, so in some sense, the picture that I gave you so far is a little bit bleak. It looks like there's not much hope of doing anything interesting by coupling these kind of light and heavy sectors in the system. But there's one kind of thing I want to return to in my last 3 minutes, which is this region near charge neutrality where we observe quite strong negative compressibility, these blue bands here. This is data from a different position, but we see the same thing at both positions. Okay. So this kind of negative compressibility, as I mentioned, you can't get it at a single particle level, but you can get it if interactions are strong, and in particular, if phase transitions are going on in the system. Now, there's kind of this fourfold multiplicity that always seems to haunt us in graphene, right? So we see 4 of these kind of negative compressibility features, and that's actually immediately suggestive of a connection to the fourfold degenerate 0th Landau level that we know should be present near charge neutrality in the Dirac, the kind of light Dirac sector. Okay? So the idea that we had is to basically kind of try to model this using a really simple and kind of crude so-called mean field model, where we basically construct a free energy by, first of all, considering the kinetic energy of some bands that I'll describe, and then we add to that a kind of mock on-site repulsion that penalizes differential occupation of the bands and kind of an exchange term that favors polarizing all the electrons into one band. If we consider this energy spectrum that we had, we said that, well, at near charge neutrality, we have an n equals 0 Landau level from the Dirac sector and actually 2 n equals 0 Landau levels from the flat band sector. Okay, so that gives us 12 levels to play with. 4 of them are from Dirac, 8 of them are from the flat bands. We only see transitions up to filling factor 2 out of 6, which means that we only need to consider actually the a total of 8 bands. Okay, and so the idea then is basically to kind of minimize this free energy. Okay, so and in effect, by allowing the system to occupy those Landau levels differently, we minimize the free energy, and then that allows us to construct the total energy and the chemical potential and so on. Now, there are these crossing points that you can see here where the gaps at the integer filling close, and these are most easily attributed to crossings at the single particle level that are induced by Zeeman splitting, okay? And so we can already, without kind of invoking anything about interactions, we can use this to put some constraints on the relative G factors on these Landau levels. I want to mention that we can only determine this up to a constant because we also need to assume an energy band offset for the flat and Dirac sectors. Here the red is the flat band, black is the Dirac Landau levels. This level diagram generates a set of gap closings at the integer fillings that agrees well with the experiment. And then if we go in and just add interactions via the prescription I mentioned, we can generate, we can kind of simulate this system and observe negative compressibility actually using some rather reasonable parameters. So the bottom line here is that it looks like this, and so I should say, just to summarize, that means that these negative compressibility regions correspond to phase boundaries with fixed number of partially filled Dirac-Landau levels. So when I've crossed the first boundary, I'm going from a situation with 0 partially filled Dirac-Landau levels to 1, and then to 2, and so on. The bottom line and the takeaway here that I have negative 40 seconds left, so let me just say that it looks like most of what we can see is explainable just by assuming a picture where the Dirac and flat sectors are basically decoupled from one another and weakly interacting, and we can kind of verify this by noting that it looks like the Dirac fermions just kind of live as they fill the gap at low magnetic field that is opened in the flat band sector. But what is interesting is that there is a region of the phase diagram where interactions become strong, and that's basically in the quantum Hall regime near charge neutrality, where we can observe these kind of unusual phase transitions that require the Dirac fermions to play a leading role. And so one hope or one dream, I think, is to see if we can think of more ways to strongly couple these two sectors and get at some of the many body physics that might be available in systems like twisted trilayer graphene. Thank you for your attention.
Thanks for the interesting talk. If there's one very fast question, we can, okay.
So I think you mentioned that the Cher number can be just understood from Dirac plus bilayer graphene flat bands. So and then you mentioned that the superconductivity is more robust in the trilayer graphene than the bilayer. So do you have any? Does this tell anything about the superconductivity, or is that like a completely separate story?
I think that what our results suggest that it's a different story. Yeah, I mean, it's not. It becomes less clear in twisted bilayer graphene, where these phases are kind of always seem to be intimately related. But maybe as one increases the layer number, one decreases the degree to which those two phases affect one another, and maybe they're more independent than we thought originally.
Thank you.
Thanks.
Okay, we have to move on because we're over time. Let's thank the speaker again.